Okay, hello there. Welcome to the directed independent learning for start of the differentiation topic on Core 3. Now, really this is going to build on our knowledge what we learned from Core 2, and at the end of this very short video I'll be asking you a question which I'd like you to bring the answer to in the lesson on Thursday. Yes, Thursday. Okay, so we know from differentiation from Core 2 that if y is equal to 3x to the power of 4, for example, the rule is that we have to bring the power, oh no, that doesn't work, classic, dy dx, we differentiate, we have to bring the power down, so we get 4 multiplied by the 3 is 12, and then we have to take 1 off the power, we get 12x cubed. We went into more difficult examples. For example, y is equal to 1 over the square root of x. That's not a problem, because we can write that as x to the power of minus a half. And then we can apply our usual rules of dy dx, this time equaling, well, we bring the power down, so that's minus 1 over 2. X to the power of, take 1 off the power, it's minus 3 over 2. And that doesn't look particularly nice. So we could decide to simplify that. Well, the minus there tells us that it's going to be a fraction. So I'm going to write that as minus 1 over the 2 there. So I'll put that 2. And it'll be x to the power of 3 over 2, which is square root of x cubed. Okay, so it just makes it look a little bit nicer. To be honest, it's not very nice anyway. Horrible looking function, but c'est la vie. What we're going to be doing in the lesson is going over some more complicated examples. Now let's consider, if we like, x plus 3 in brackets all to the power of 4. Now if we differentiated this, we'd have to multiply the brackets out. Okay, we'd have to multiply the brackets using the binomial theorem, which is a bit of a pain. So it'll be x to the power of 4. Correct, I need my Pascal triangle here. Commissions, not enjoying this already. There must be a better, easier way to do this. There we go. So it'll be plus 4 lots of x cubed multiplied by 3 to the power of 1. Remember this? Yeah, you do. Then it'll be 3 squared plus 4 lots of x, 3 cubed plus 3 to the 4. Which, if we simplify, x to the power of 4 plus 12 x cubed plus 9, 6 times 9, 54 x squared plus, I'll blink in it, 27 times 4 is 80, 108. Let's get this. 27 times 4, apologies for this. 80, yep, 108. X plus 81. So we've used the binomial theorem to expand that out. Now we can differentiate each term by itself. So it'll be 4x cubed plus 36x squared plus 108x plus 108. Bare missions. Okay, bare missions because we have to use the binomial expansion. And imagine, I mean, it's not too bad for when it's power of 4, but imagine if it was power of 6. Imagine if it's power of a half. Then we don't actually have a finite binomial expansion for it. We've got problems there. So there must be an easier way to deal when we have functions involved in brackets. Okay, so let's consider y is equal to 2x plus, now I'll use a minus, underrated minus signs, to the power of a half. Okay. Now we should be thinking, this shouldn't be too hard. We can differentiate 2x minus 1, and we can also differentiate the whole thing to the power of a half. Trouble is with the half, we cannot have a binomial expansion, finite binomial expansion for it. So how do we differentiate functions like this, where we have an inside function and an outside function? The inside function, which we're going to call u, is 2x minus 1. The outside function, which is y, well, it's basically u to the power of a half. Okay? We've got two functions here. We've got our inside function, 2x minus 1, and we've got our outside function, which is the something to the power of a half. Now, we can differentiate these. This is not a problem. Okay? If we differentiate u with respect to x, so du dx, well, 2x differentiates to 2, and minus 1 differentiates to nothing. Okay? Now, this time, for the outside function, we have to differentiate with respect to u. So this becomes half u to the minus a half. Okay? Now, this is the beauty of this method. We take a look at dy du, and we multiply it by du dx. We basically multiply these two things together here. What was our result be? Well, if we treat these as fractions, the du will cancel with the du. So what we're left with is dy dx, which is what we're after. So, dy dx has to be equal to, well, it's dy du, which is half u to the minus a half, multiplied by 2. Du dx. 2 there. Okay? Now, if we simplify that, the half will cancel with the 2 there, so we're just left with u to the minus a half. Now remember, u is 2x minus 1. So what we're left with is 2x minus 1 to the power of minus a half, which if we wrote a little bit more nicely, would be 1 over the square root of 2x minus 1. What we've employed here, this rule here, is what we call the chain rule, where we have an inside function and an outside function. The rule is we differentiate the inside, differentiate the outside, and multiply them together. Okay? Now we don't have to go through this formal thing of writing u is equal to 2x minus 1, y is equal to u to the half every single time. I'll show you another function, and we'll do it with x squared plus 4x minus 2 to the power of minus 2. Okay, we'll deal with that one. Now, eventually you'll be able to do these by inspection. dy dx. Right. Here we have something, which if I get my highlight, this is our something. Our something is to the power of minus 2. Okay, our something is to the power of minus 2. So if we differentiate that something to the power of minus 2, the minus 2 comes in front, and we subtract 1 from the power. We do then have to, however, multiply by what the inside bit is differentiated. Okay, now the inside bit differentiated is 2x plus 4. Okay, so this bit here is differentiating the outside, the dy du in our previous example, if you like. This dy du, lost my pen there. This bit here is multiplied by the derivative of the inside. Now I think we should tidy this up a bit. So the minus 2 is on top, but we also have this 2x plus 4 on top. So we end up with minus 4x minus 8. Okay. Now at the bottom we have this minus 3, so it will be x squared plus 4x minus 2 to the power 3. Okay. Which I might even decide to tidy up a little bit more. Just keep one minus sign. I don't know why we don't like minus sign. Underrated, as I've said before, but there we go. I think that looks even nicer. Okay. We can then, if we think about this curve, if we think about this as a curve, we can then find the stationary points of this curve quite simply. because at the stationary points, dy dx is equal to 0. Therefore, minus 4x plus 8, things given out, x squared plus 4x minus 2 cubed is equal to 0. Now, the denominator can never be 0, we cannot divide by 0. If we multiply both sides of this equation by the denominator, we just end up with minus 4x plus 8 is equal to 0. Therefore, it's not rocket science to do this, minus 4x minus 2. And our y value for our stationary point is going to be, well, it's going to be 2 squared, which is 4, plus 4 lots of 2, which is 8, minus 2 to the power of minus 2. Substituting it back in, just as we would in core 2. So we get 12, 10, so 10 to the minus 2, which is equal to 1 over 100, 0.01. So our stationary point has coordinates minus 2, 0.01. Not going to classify that yet because we need to know a bit more knowledge because we need to differentiate dy dx. We can't do that one yet. But that is essentially the chain rule. So, your question. Y is equal to x squared minus 7x plus 3 to the power of a half. Okay? I want you to find dy dx and the exact coordinates of the stationary point. Okay? By following through the method. Differentiate this something. Here we've got the something to the half. Bring the power down.